Very good. Welcome back. What we would like to now do is to continue with our discussion. I'm going to bring back my tablet, and we're going to discuss the Lie derivatives of covectors and of the metric tensor. So how do you compute those? What are the formulas for those? And the idea is going to be very simple. We write the Lie derivative of something in two different ways and we equate them. And so the first thing is going to be if we have a covector which we write, the components have lower indices, and then the basis covectors are written like that. And we have a vector, let me call it U. The vector U has components, and then it has basis vectors. Let's write it U, J, E, J, like so. So if we have something like this, then with the action of the covector on the vector, because remember the covector is a linear functional, that means that we can write it, well, these are components, and here we have the basis covectors, and these guys act on these guys here. These guys being linear functionals, I can pull out the uj, pull out those numbers, bring them outside, and now we have the action of this basis covector on the basis vectors, and we saw that this is a Kronecker delta. So the net outcome of that is we have an expression of this form. Okay, very good. Simple, familiar perhaps to you, but the point is that the action of a covector on a vector gives you something that is a scalar. This is invariant. This guy transforms in a particular way under changes of coordinates. This guy with the upper index transforms in the opposite way, so that this is invariant under changes of coordinates. So how do we compute then the Lie derivative of something like that? Okay, the first idea is that this is a scalar operator, and this is a scalar. We know exactly how this would act on scalars. On the one hand, then we have this acting on this scalars, and we know how to do that calculation. This would be just V Vj dj, that's the vector. This is just the derivative. Maybe we can write it as V acting on this particular product, and this is just a derivative. Here is the vector, and so this is going to act on the first guy. Well, let me just write them all out for now. For now, this is all we do. But there is another way to compute this Lie derivative, which is to use the Leibniz product rule. The derivative of omega u is going to be the Lie derivative of omega, which is what we want to compute, and which is, because this is a scalar, this is just going to be a covector acting on the vector u plus omega acting on this Lie derivative u. And since this is a scalar operator, this is a vector, so here we see a covector acting on a vector, same thing. So we have two different ways to compute the same thing. Let us subtract one from the other, and what we get is that the Lie derivative of V acting on omega U. Well, maybe before we do that, it's better if we just compute these guys here. Let me check. Yes. Let me write this as this guy here with an I, just to the various components, and this guy here, omega I LV U I. Now we have an expression for this guy here from the previous class, so we're going to substitute it there. And so when we equate these two expressions here, this one and this one, what we're going to get is something as follows. On the left hand side, we have Vj dj omega I ui plus Vj dj, sorry, dj omega I dj ui, and on the right hand side we have this expression here, the derivative omega I ui plus omega I, and now we're going to substitute the expression for the components of the Lie derivative of a vector, which are an Vj dj ui plus minus, actually it's a commutator, uj dj vi. When we see this, we see that this expression here has a Vj omega I. These two terms are exactly the same, so this one cancels this term here, and then we end up with, let me just take the derivative and rearrange, Lv acting on omega component I ui equals Vj dj omega ui plus omega j ui di vj. And because this is supposed to hold for arbitrary choices of ui, for arbitrary ui, we can actually just write what the coefficients are supposed to be. And here we are, Vj dj omega plus omega j ui, no i's there, d I v j. The trick is always the same, so I'm going to do it one more time and compute what the Lie derivative of a metric tensor is supposed to be like. This is important because we're going to use it for deriving quantum mechanics later. So the idea is, so the Lie derivative of the metric. Suppose you have a metric tensor and you act it on two vectors. Let's call them A and B. A metric acting on two vectors. Remember, a tensor is a linear function of this, so we can pull out the coefficient. So let me write it explicitly just to remind you how this works. If you have AI, EI, and BJ, EJ, those are the two vectors. This being a linear function of whatever appears in those slots, the components, the numbers AI and BJ can be pulled out. And whatever remains is the metric tensor acting on the basis vectors. So this is just the scalar product of the basis vectors. This object here is what we call the components of the metric tensor. Very good. So if we want to act on, if we want to figure out the Lier derivative of the tensor G, what we do is we realize that we can compute it in two different ways. We can compute that by saying whatever this is, it is a scalar. So if it is a scalar, we do V acting on these three guys. And these are just derivatives. Vk, dk acting on Gij, Ai, Bj. So that's what this guy is. On the other hand, this guy acting on GAB, the idea is we're going to use a Leibniz rule on it, and we're going to say it's the derivative of the first acting on the two others. And look what I'm doing here. L, the Lier derivative, is a scalar operator. So when it acts on the first, if this was a tensor, then this object is the same kind of tensor. If this was a tensor that acts on two vectors, this object is a tensor that acts on two vectors, and we see the two vectors there. So that's the first term, but we're also going to have G acting on the Lier derivative of the first vector plus G acting on A, the Lier derivative of the second vector. When we equate those two, and of course here you can probably see that this actually is we know what these various the Lier derivatives are, right? We have the components of these vectors. We have the components of that vectors. So if we have the components of those vectors, we can compute these scalar products using just that formula. So all of these guys are something we can compute. This guy, however, has this object, which is what we want to find. But this guy here, this is the Lier derivative of a scalar. We just computed it. So we do some algebra, and then we get, so doing the algebra, we obtain an expression, and the expression is something like the Lier derivative of V G, which is a vector Ij, a tensor, is actually V K D K derivative of Ij plus G I K derivative J V K plus G K J derivative I V K. So we do the algebra, and of course the A and B have disappeared here just because being arbitrary, we can just pull them out. Very good. So that's what the derivative of the metric tensor is going to look like. Please notice that here the only thing I have used about the metric tensor is that it is a tensor. This would be valid for any tensor t, right? And so because this is a scalar, you can do exactly the same thing, and the same things go through there. This is valid for not just the metric tensor, but for any tensor with components Tij like that. Any tensor which has two slots for vectors. Very good. We have some of the tools now. Now we can start trying to think about what it is we're trying to do. So I'm going to talk next about the cotangent bundle. The cotangent bundle. This is a funny space that we want to talk about. So basically we have several spaces of interest here. One of these spaces is the simplex. The simplex is the space of probabilities. Just coordinates theta, as many as you need, n dimensions. Another space that you may consider now is once you have the simplex, so let's call it S, you have tangent spaces for vectors here. Maybe my figure didn't come out right. For any curve, you have tangent vectors. If you consider all the possible tangent vectors at one point, you have the tangent space. This space here, the tangent space at the point theta, we write as the tangent space to the simplex at the point theta. Very good. This is why do we care about vectors? These are possible velocities, right? Now, if you imagine what happens with the set of not only the simplex, but all the possible tangent spaces that you have there. So you have this base space, and at each point you have the various tangent spaces. This is called the, it's a fiber bundle. A fiber bundle. It's as if you have the base space with lots of fibers, and the fibers are these n-dimensional tangent spaces. In this particular case, it's called the tangent bundle because it's the space, the basis space, S, the simplex, plus all the tangents. The tangent bundle, and we write it as just T S. All right, this is the tangent space at one point. The tangent bundle is all the tangent spaces. There is a third space that we can consider, which is the space, and I'm going to write it like this too. At each point, you put the space. Let me do it in the next page. At each point, you consider the space of all covectors that you could imagine. The better way to think of a covector is in terms of little lines like that, because it's like a gradient, right? Covectors are a gradient, so you have one possible gradient, here you have another possible gradient. The space of all possible covectors is called the cotangent. It's a space of covectors. The cotangent space at the point theta. This is written like T star S at the point theta. And of course, what we would like to go for is this space that includes the basis space, and all cotangent spaces. This is called the cotangent bundle. It's a bundle of tangent spaces attached to the base manifold, and that's written as T star S. Why do we care about the cotangent spaces? These are momenta, or they will be momenta once we're through with them. Very good. The interesting facts about this is that there are several spaces here. One of them is the space of microstates. You could call that the space of microstates. If you have a three-sided die, it says 1, 2, 3, right? This is what we normally call the configuration space. In classical mechanics, it would be just the positions and momenta of the particles. Configuration space. These are the objects that are supposed to be real, right? The probabilities are all in your brain, the epistemic objects. The stuff that's actually real is the faces, 1, 2, 3 of the die. So it is not a bad idea to call this the ontic configuration space, because it is the configuration space of the things that are actually real. That's one of them. Another space that's useful is the space of probability distributions, the simplex. The simplex. So the simplex is also a configuration space. It's the configuration space for probabilities. So we're going to call this guy the epistemic configuration space. Well, why do we need to have these names? Well, if you're studying in classical mechanics and you're studying trajectories, you want the trajectories in the configuration space of positions. Well, here, if you want trajectories on the simplex, on the space of probability distributions, you will want the trajectories on the configuration space of probabilities, which is the epistemic space. And so we could actually, to simplify the notation a little bit, we're going to call this the E configuration space. Apart from that, we also have the tangent bundle, right? Which is the space of probabilities and the vectors and all the tangent vectors, right? That one we're not going to have much use for, but the cotangent bundle, let's just write by what it is. This guy here, this is the guy that's going to be, remember, we want curves in configuration space. For curves, we would like to have velocities and the momenta. Okay, we want positions in the space, probabilities, and momenta. This is going to be called the E phase space. I hope you appreciate that I'm setting the tone for dealing with doing Hamiltonian dynamics on the space of probabilities, right? But we're not doing physics yet, right? This is just, we're playing with the geometry of these spaces. Very good. Once we have these vectors and covectors and all of these spaces, we have to start doing some mathematics on this space, the cotangent bundle. It turns out, and this is why this space is interesting mathematically, it turns out that these phase spaces have a very, very interesting geometry of their own. They have interesting structures, and that is what we want to exploit. The fact that we're dealing with probabilities adds an interesting layer in that beyond the structures that are typical of phase spaces, of cotangent bundles, here we have the additional information geometry of the simplex. So we have more than people who just do cotangent bundles. We have the cotangent bundle plus the information geometry. So that's what we're going to be doing over the next few lectures. But before we do that, let me continue with some notation so as to have a way to talk efficiently about these things. Notation. Vectors, covectors on the cotangent bundle. Before we are doing vectors and covectors just on S. Now we're going to have some more. And so the way we're going to represent a point first. A point X in the space T star S on the cotangent bundle will have coordinates. We're going to write it as X is going to be theta pi. The coordinates of say, okay, listen, look where this is going. Positions in this space and the corresponding momenta, right? So that those are going to be the pi's. But at this point, we do not know that, where theta stands for the end coordinates on the simplex, and pi stands for the n coordinates. Remember, this is on the cotangent space at the point theta. So these are supposed to represent, this is supposed to represent a covector at the point theta, right? If I tell you the basis point on the manifold, and then I have this cotangent space, and I give you the coordinates there, I can give you the coordinates of every point in this manifold. You can appreciate that this phase space has 2n dimensions, right? If this guy has n and that has n, this guy has 2n dimensions. But I'm not going to tell you that yet, because we're going to have to think a little bit harder about this in a second. Okay, a curve on this cotangent space, a curve on TS is going to be given by the coordinates x as a function of lambda. Lambda is a parameter on the curve. This is going to have its own coordinates, theta as a function of lambda, pi as a function of lambda. And we can do vectors. So a vector then, a vector on this space, a vector v, is going to have components. And we're going to write these components as, well, v is going to be d lambda, right? If you take the vector that's tangent to this curve, that's what it's going to be. And we're going to write this guy here, v, as you take d theta d lambda and then d theta plus d pi d lambda d pi. So now you see that you have 2n basis vectors, n coordinates and n dimensions for this part, which is what you would have if you had just the base manifold, and then this for the part on the cotangent spaces. Very good. A tangent, a directional derivative. So you can appreciate that we're doing this in exactly the same way we were doing it before, except that now we have twice as many dimensions. The directional derivative, the lambda, is going to be take the derivative with respect to theta, and then the theta, the lambda, plus the derivative with respect to pi, and then the derivative of pi, the lambda. And this is the kind of object that we would like to be able to write as the components of the gradient multiplying the vector. So we're going to write this as the gradient of f acting on the vector v that had those components. All right. Now, this gradient, you can probably see that the gradient has components along the thetas and along the pi's. So I'm going to write it with a little squiggle there to distinguish it from the gradient that has only components along the thetas, the part that just acts on the base manifold. So this, remember, is the gradient on the full cotangent bundle. Very good. We need a little bit of a more useful notation, and we're going to use this expression here with the x's. A better notation here, so that we don't have to keep writing thetas and pi's all the time, is then going to be let x, remember what we have here, we want these guys to be at some point, we're going to write this as theta I pi I. So what I would like to be able to say is that you have two types of x's. Both go with i's, right? So the same I here. So we're going to write this as 1 I and this one as 2 I. So the advantage of writing something like this is that we have the 1 and the 2 that tells us that we're dealing with a theta or a pi. So we're going to have a composite index alpha I. Alpha takes two values, and this refers then to thetas, and that refers to pi's. And the advantage of doing something like this is that then vectors take a very simple form, which is that vectors can be written with these composite indices, and this guy here is going to be the basis vector, and this guy here we just write as the x alpha I d lambda, which is equal to d theta d lambda, and then d pi d lambda. It has the two values. This guy comes with two values depending on whether it's going to be theta or pi. Another little advantage of all of having this alpha here is that the alpha tells you whether you're dealing with theta, which has an upper index, or pi, being a covector, has a lower index. So by now, with this alpha, we keep track of which one is which, and so we no longer need to worry about which one is up or which one is down. We're just going to use whichever is most convenient. They mean exactly the same thing because really we're going to be dealing with these basis vectors and those basis components, and so that will tell us whether the I is going upstairs or upstairs. I think that we are essentially ready here. We can actually figure out some other expressions, but they're sort of like trivial. Like, for example, we can rewrite the lambda, which is the gradient of f acting on v. We can write this as the f dxi, which is the components of the gradient, multiplied by b alpha I, right? And the gradients of f, we can write them as the components of the gradients and then the basis gradients, which are those guys here. So we have it. We have all the notation we want now. So now, next time we're gonna put this to good use. Now remember where we started in all of this. So we're done for today. I would like just to remind you that what we are trying to deal with is probabilities, but we are, to simplify life, we are slicing our probabilities so that the probability of x is being written as the probability of an, let me see, do it better. The probability of x in a small interval delta x is being discretized into a pi, okay? Now, with this notation of having a large number of i's and also this extra index here that tells you whether you're dealing with the coordinates or the corresponding momenta, with this we can actually deal with essentially continuous probability distributions of any type. So the notation that we have here when we write expressions like this can easily be transformed into integrations, because each one of these guys here can be transformed into something like that, and this will lead us to integrations. So we can easily make the transition to continuous spaces. But now, time to stop. The crucial thing is going to be how we draw curves on these spaces and what are the curves that have particularly beautiful properties, because after all that's what quantum mechanics is all about. It's a theory that's filled with particularly beautiful properties. That we do next time.